All right, so this practice problem is going to look at the construction of a wall. So imagine that we have a 17-meter high, 11-meter long wall, and it's under construction, and it's braced as shown. So there are these 10 braces along the length of that wall. The wall is in stable equilibrium without the bracing, but it can still pivot at the base. Okay, so we're going to imagine it pivoting at the base. Suddenly we have a strong wind, 650 newtons per square meter of a wind blowing on that wall. So what we want to do is know what are the forces by each one of those braces when we have that strong wind. All right, so we're told that the force of the wind is 650 newtons per square meter. So we need to know what the total force of the wind is. In order for us to do that, we got to know what the square meter size, what the area of that wall is. So the area of the wall we know is the length of the wall times its width of the wall. So that's 11 times 17, and we get an area of 187 square meters is the area of our wall. So the net force by the wind is going to be our 650 newtons per square meter times my 187 square meters, and that gives us a net force of 1.22 times 10 to the 5th newtons. So the total force of the wind acting on our wall is 1.22 times 10 to the 5th newtons. Now we're going to explore this problem as a torque analysis to see if this is in static equilibrium, what force is that each one of those braces acting. And so for a torque analysis, we of course do an extended free body diagram of our wall. So let's draw that wall, and we'll draw the forces acting on it. We know we have the force of the wind. That's going to be our net force acting on that wall. And as stated in the problem, it's acting halfway up that wall. We also have the force of each one of those braces. And so we're going to draw, they also hit at that center point. We want to keep in mind that there are 10 of those. They also hit at that center point as depicted in the picture, and they're pointing up and to the right. If we imagine them holding up that wall as the wind is trying to blow it, that force is up and to the right. Now the wall also has a weight. We know that that weight is going to act at the center of mass. If the wall is in static equilibrium, in equilibrium without the braces, then that center of mass is directly over the base. That's that idea of balance. And if it's directly over the base, it's not going to induce a torque. So we could draw it on there. I don't exactly know where the center of mass is located for this wall. It doesn't indicate that it's at the geometric center or that it's uniformly distributed. But because it will not induce a torque, it won't induce a torque because it's along the line of our pivot point. We're going to identify this as our pivot point. I'm going to leave it off of our picture since it won't cause a torque in our system. Similarly, the wall is being held up by the ground, and so there's also a force of the ground. Since that's at the location of the pivot point and also pointing straight up, it too will not induce a torque. And so we're going to leave that one off our picture as well today. All right, so we have two forces that we're going to examine the torques of so that we can get the idea of what that force of the brace is. So torque number one, we know is force 1 times the radius of 1 times the sine of the angle. Well, force 1 is the force of the wind. The radius is the distance between that pivot point and where that force is acting. So here's the radius 1. And that angle, if we extend that radius, curl to the force, this is theta 1. So we know that that wall is 17.5 meters high. So the radius is 8.5 meters. And this angle is negative 90 degrees. So our torque 1 is 1.22 times 10 to the 5th times 8.5, and the sine of negative 90 is -1. And indeed, the force of the wind would cause the wall to rotate in a clockwise direction, which would in fact give us a negative torque. So the torque by that wind is minus 1.037 times 10 to the 6th Newton meters. All right, that's torque number 1. Torque 2, of course, is force 2 times the radius 2 times the sine of the angle between those two. Well, the force of those braces, we have the force of the brace. We have 10 of them, so I'm going to multiply the force of any one brace by 10. It too is acting at that same radius, so this radius 1 is also R2, so the distance between the pivot point and that force acting. So that is 8.5. And the sine of the angle, so what is that angle? I put my fingers in the direction of the radius and I curl in the direction of the force. That is this angle here. That is angle number 2. And that angle is 35 degrees. I did forget to draw that in my picture. That's no good. This is 35 degrees. That's a given parameter in the problem. So I apologize, that was not in the picture. That is 35 degrees. If that's 35 degrees, that makes theta 2 also equal to 35 degrees. And again, that was given in the problem. I just missed it in my picture. So we have the sine of 35 degrees. It is a positive value because as we curl in that counterclockwise manner. This will give us a positive value, and indeed, force number 2 is exerting a torque in the positive direction. So we end up with value of 48, if I multiply these out, 48.75 times the force of any one brace. So we sum these two torques together. That net torque is going to be 0 if we're in static equilibrium. And so we have negative 1.037 times 10 to the 6th plus 48.75 times the force of a brace. We end up with 1.037 times 10 to the 6th is equal to 48.75 times the force of any one brace. And that allows us to solve for that brace force of 2.13 times 10 to the 4th newtons. All right, so recognizing the situation that we have, keeping in mind that the force of that wind was given as newtons per meter squared, so we had to, of course, recognize I have a large surface that force is being applied across. Looking at the free body diagram, extended free body diagram, and recognizing which forces are exerting torques, and using that idea that in equilibrium, the net torque is equal to 0. So those forces causing a clockwise rotation must equal those forces causing a counterclockwise rotation, such that the sum is equal to 0. All right, good job.